So, hello to everyone who's watching on YouTube. I am waiting for a few students to join the session in person. So, I guess I'll get started in like 5-10 minutes so that a few students join the session in person also. Okay, so I guess we can get started now. So I think Manas has joined. So hello Manas, just to reintroduce myself, I'm Lakshay Sagi, the problem solving TA for the NPTEL Games and Information course for the Monday 6 to 8 p.m. sessions. So this will be our sixth session, and in this session, I'll be discussing problems related to like whatever was discussed this week, which was mostly like dynamic games and stuff. So not like not a lot of new concepts were covered except for dynamic games in this week, but yeah, we'll be trying to solve problems related to those. Uh, I'm a bit unwell today, so uh, like I think this will be a short session, but still just bear with me as long as the session goes. So also like if you have any doubts at any point of time or are there any technical issues, then feel free to inform me via chat and I'll try to rectify the same as soon as possible. Okay, then maybe I can just start by sharing my screen to so that we can discuss the questions. I'll just share my screen then. Also, like throughout the discussions, like I'll be assuming while discussing the questions that you guys have indeed gone through the um, lectures for the week. So I won't be discussing the theory. I'll be discussing the problems only. So I'll be assuming that you have gone through the theory. So just as a convention which we'll be using. So like, this is a pretty common convention that in a zero-sum game, the column player is maximizing his payoff, and in a non-zero-sum game, both players are maximizing their payoff. Though I don't think we'll be needing this as much, but yeah, just it's a convention which is usually adopted. So maybe we can start with some warm-up questions just to see if we understand the theory properly. So there are a few true-false questions just to start off as a warm-up. So the first question says that every simultaneous game can also be modeled as an extensive form game. Is this statement true or false? So, Manas, uh, uh, do you think this statement is true or false? Like, no one's grading you, but just asking. Okay, so Manas is saying that the vice versa is true. That an extensive form game can be modeled as a uh, simultaneous game. So yeah, actually this is the second question, right? One is that every extensive home game can model the simultaneous game. So good job. One is like this is actually true. Like this was also discussed in the lectures, right? Uh, but actually, like this was straight from the lectures, but this also that every simultaneous game can also be modeled as an extensive form game. So actually, this statement is also true that all every simultaneous game can actually also be modeled as an extensive form game. And why am I saying that this is true? So intuitively, you can think of it in this manner that what is actually simultaneous game actually like you are planning a strategy while playing a simultaneous game, right? So while playing while thinking about your strategy, what you are actually thinking about is okay, so suppose they have two players and player one is thinking about if I play something, then what will the other player, what will the player two play, and in response to that, what should I actually play as player one? But then again player two can change his response. So in that condition also, like what should I play as player one, so that player two's response is something else, and then to the player two's new response, I can again start thinking that what will be my new response to that player one. So yeah, actually, Manas, yeah, we don't know any sequence of playing, but just like what we discussed in the lectures, that every extensive form can be modeled as a simultaneous game. So here, what we did was remember that like okay, maybe I should not write down, but just maybe we can discuss orally also that in an extensive form game, like even though the play comes afterwards, the strategizing has to be done before the start of play, right? We have to decide the strategy which we are going to play before the play starts. And this was the reason why an extensive form game could be modeled as a simultaneous game. This was precisely because in a simultaneous game also, uh, we are strategizing at the start. So in terms of strategies, like because of this strategizing at the start thing, extensive form game could be modeled as a simultaneous game. But note that this goes both ways, right? So we have to decide a strategy at the start of extensive form game, and we have to decide a strategy at the start of simultaneous game. And suppose there are two players, then player one in his mind will think that, okay, like if I play something, what will be the also, we are assuming here that both the players have perfect information. Like player one has information about player two utility function, player two has an information about player one's utility function. Yeah, note that it makes sense only when like players know their utility functions, like each other's utility functions. If one player does not know the utility function of the other player, or then you can't predict what the other player will play, and then you can't really strategize. And yeah, then you will be playing differently. But right now we are assuming that we have perfect information. And yes, exactly. So choosing of plan before the game starts. Yes, and that's exactly why, like, this is why extensive form game was modeled as, could be modeled as simultaneous game, because we could strategize before the game starts. But this goes both ways, like uh, before the game starts, deciding on a strategy is equivalent to being simultaneous, because both the players are actually deciding the strategies simultaneously, right? Even though the decisions are in a dynamic manner, but the strategies are simultaneous. And that's why this is also true. So good job, Manas. So this is true, as this is similar to modeling extents. Uh, yeah, maybe I should write something. The reason is similar to that of modeling extensive form game as a simultaneous game. The key idea is that strategies for the simultaneous as well as extensive form game are decided before the play actually starts. So, okay. So, Manasa, you're saying that in simultaneous game, how do we derive tree? Information is not revealed. So, Manasa, like you can what one can assume in these games uh, is that is the argument of is the argument of rationality or something like uh, like we are not considering right now about threat equilibriums or something like that. We are only considering the arguments of rationality that each player wants to maximize his or her payoff, right? So as player one, even though I don't know what the other player is playing, I can still assume that suppose it's a zero sum game, or like maybe suppose it's any game. Then as player one, what I know is if I make some decision, if I play, let's say we are rolling a dice and or let's say we are just writing down some number as a player, and so suppose the game is something like this, that two players like player one and player two both will write down some number, and the sum of those two numbers, if even then player two wins, if odd then player one wins. If it is something like that, then I know that as player one, if I write something like a two, then player two will play something like a one, or something like a two. Like player two if I play an even number, player two will also play an even number. But in response to that, as a player one, I can instead play an odd number. So in that, with that kind of an idea, like information is not revealed to us what the other player is playing, but we can derive what the other player will play because we are assuming an argument of rationality. Like till we like we are not talking about threat equilibrium right now. We're talking about arguments of rationality that every player wants to maximize their payoffs, let's say. And so then you can predict, right? Even the information is not revealed, but if you know the other person is trying to maximize his payoff, uh, then you can predict what the other player will be playing, right? Does this make sense, Manas? Okay, that's good. Yeah. So the high level idea is like even the information you don't know what the other player will actually play, but you can predict what the other player will play actually because like we are assuming that players want to maximize their payoffs. And yeah, so this is the high level idea. Okay, then. Then maybe we can move on to the third question. So third question says that consider a full information extensive form game with no random nodes. Okay, I think anyways like randomization has not been talked about in full information extensive games yet, right? So yeah, you can assume like there are no random nodes and every node will have deterministic choice. So the optimal strategy obtained by using backward induction corresponds to a Nash equilibrium strategy in the standard normal form of the extensive form game. So what do you think, man? Is this statement is true or is this statement false? So basically like like the optimal strategy obtained by using backward induction. So this is the strategy which I was talking about recently that the this is the strategy which you did which you can like predict what the other player will play because like this is the strategy you derive by thinking that other player will always try to maximize his or her payoff. So the optimal strategy obtained by using backward induction. This is the strategy which will be played assuming that player wants to maximize his or her payoff at every step. So does this strategy correspond to a Nash equilibrium? This kind of setting was also, I think, discussed in the lectures, if you remember, Manas. Okay. Okay, so you're saying you're not sure what kind of Nash equilibrium. So Nash equilibrium, the definition of Nash equilibrium is a very standard definition. Like uh, so there are usually like there's nothing like kinds of Nash equilibrium. So usually the definition of Nash equilibrium is pretty fixed, and the definition of Nash equilibrium is that a set of strategies which will be like players playing a set of strategies so that no player wishes to change his or her strategy. So this is what you mean by Nash equilibrium, that a set of a strategy profile, basically like a set of strategies played by the players, such that no player now wants to switch their strategies from the present strategy to another strategy. Okay, so Nash equilibrium is Nash equilibrium. Like it does not depend on like threat or rationality based arguments. That's what I'm saying. Like like a threat like threats is a different thing. Rationality based arguments are like different things, and Nash equilibrium is another different thing. Like rationality based argument, the definition of rationality based thinking is every player will want to maximize his or her payoff at every step. Threats are something like a player may play suboptimally, uh, so that to ensure that the other player also plays suboptimally. So threat is basically like kind of saying that you will be a player is playing suboptimally so that other player also gets somehow. Where a rationality based argument is something like one player is always trying his or her best for himself. But the Nash equilibrium is the third thing, and Nash equilibrium is a like very standard concept across multiple games. And Nash equilibrium means that uh, a set of strategies such that no player wants to switch his or her strategies. This is what you call Nash equilibrium. So these three are different things. Does that make sense, Manas? Like, why is Nash equilibrium? Like, definition Nash equilibrium is just this, that a set of strategy profiles by different players so that no player wishes to switch to another strategy. It does not depend on like rationality based or threat based, just this definition. Okay, so then in that case, what do you uh, think? Uh, so this is the rationality based or the one where you try to maximize at every step. So this is the strategy obtained when you try to maximize at every step, the optimal strategy obtained by backward induction. So does the optimal strategy by backward induction correspond to Nash equilibrium strategy? Yes, exactly. So then Nash equilibrium is true. So good job, Manas. So this was also discussed in the lectures only that uh, it was discussed in the lectures that yeah, like the this backward induction will correspond to a Nash equilibrium. Okay, so I see someone else has also joined the meeting. So hello, Shobana. Okay, I think it is in week 6 only. No, Manas. Hmm. Okay, never mind. Like, even if I think it is in like, I think like this question is like these kinds of things were discussed in one of the lectures where like the threats and everything was discussed. Okay, okay. Extensive game discussion starts from week 7. Okay, have I? And okay, maybe I'll just make a quick check, like, because I believe, like, okay, like maybe just if you assume like whenever I'm talking about extensive form game, just think of it as thinking about a dynamic game. That's what I'm saying. Like for now, let's just think of extensive games as dynamic games, and then like, does everything make sense? Whatever we are discussing right now, like all these kinds of things, whatever we discuss right now, does that make sense then? Right? Because like all these, I believe, were discussed anyways in week 6. Like with respect to dynamic games, this was discussed, right? That simultaneous, like a dynamic game can be modeled as a simultaneous game. Basically, a simultaneous game being modeled as an extensive form game, and like full information dynamic game corresponding to Nash equilibrium strategy. So I think in that sense, this was all discussed in week 6 itself. Uh, is it fine, Manas? Okay, I assume that it's fine. Then like then I guess we can move on to the fourth question. So this was also um like this kind of a problem was also discussed. Like this was also discussed in the lectures that consider a perfect information extensive form game. So with no random nodes, every Nash equilibrium in the normal form of the game corresponds to the strategy profile obtained from backward induction. So what this is essentially saying is this statement is claiming that every Nash equilibrium corresponds to uh, the backward induction on extensive form game. So what this statement is saying is Nash equilibrium, every Nash equilibrium is actually actually can be obtained by like basically doing the best at every step. Like this is the rationality based. kind of equilibrium, or like, yeah, this is the strategy profile which one gets by using rationality. And like, does Nash equilibrium correspond to this backward induction? Yeah, dynamic program kind of thing. So does every Nash equilibrium correspond to this rationality based argument? Like here we said that every like dynamic programming, or let's say the rationality based, every rationality based strategy profile which is obtained will correspond to a Nash equilibrium. This is what we said here, that this statement is true. But is the opposite of this also true? That every Nash equilibrium corresponds to strategy profile. Okay, so Manas is saying that based on 3 questions, it seems true. So actually, Manas, this is false. Yeah, like this is not true. And uh, this was, I believe, also discussed in the lectures, like when threats were discussed, right? So when threats were discussed in the lectures, uh, when threats were discussed in the lectures, it was discussed that uh, playing suboptimally can also give us some Nash equilibrium. Like if you go into the lectures, if you go into lectures when threats were discussed, so there was an example where one player trying to play suboptimally. Maybe I can try to recreate the example, but yeah, let's skip that for now. Maybe you can just check it from the lecture itself. So when threats were discussed, it was discussed that maybe a player can give a threat, and like uh, that threat is actually like, even though the player is playing suboptimally, that is also a Nash equilibrium. Like you can obtain one Nash equilibrium, like basically a strategy profile from which no player wants to switch. Like, so you can obtain a Nash equilibrium, even though it's not a rationality uh, based equilibrium kind of a thing. So it's not a rationality based equilibrium, but it is a Nash equilibrium. So yeah, there's that. The rationality based equilibrium and the Nash equilibrium are two different things, and what we are talking about is Nash equilibrium. So actually, so basically what we have is every rationality based equilibrium is a Nash equilibrium, but every Nash equilibrium actually is not a rationality based equilibrium. And this is why like why you obtain what you call the threat equilibrium, right? So threat equilibrium is precisely that kind of an equilibrium where someone is giving a threat. And what's a threat? Basically, it's kind of playing suboptimally. So if you have if you are playing suboptimally, but still it's kind of a equilibrium, like no player wants to switch it. If it's still kind of a Nash equilibrium, then that's what you call a threat equilibrium. If I'm making sense. So this was actually also in the lectures. There exists threat equilibrium which are Nash equilibriums, but cannot be obtained by backward induction. So yeah. So I hope this kind of statement makes sense, that there exists certain kinds of equilibrium, what you call threat equilibriums, which are Nash equilibriums, but cannot be obtained by backward induction. Okay. So I guess after this, like these were just a bit of theory questions, like true or false, just to revise whatever was discussed. And now maybe we can try to do some numericals. Okay. So we have this common data for questions 5 and 6. And yeah, then we'll be having these questions. So common data for question 5 and 6 is this, that let tau be an extensive form game with layers 1 and 2, whose set of outcomes O can be partitioned into 3 parts, which are namely like, so basically we have a game with layers 1 and 2, and the outcomes can be partitioned into 3 parts. player one wins, player two wins, or if it's a draw. And Okay. Uh, okay. Hello to everyone who's watching on YouTube. So sorry for that break. My network kind of suddenly broke down. But there was a network outage, but now it's like my network is up again. So hopefully there won't be any more issues. So then I guess I'll just share my screen again and hopefully the people also who joined. So people who joined the session previously join back again. Meanwhile, I'll share my screen and start discussing. Okay. So yeah, back. So should I yeah, maybe I'll wait for like 2-3 minutes so that the students who were previously present in the meeting but they also went away due to me dropping out can hopefully join back. So maybe I'll get started in 2-3 minutes, just waiting for the people to join back. Okay, maybe I can just get started. If anyone joins between the session, I'll just brief them to whatever's been discussed till now. Okay, so we were at the fifth question. So like after doing these warm-up questions, now we are at this fifth question, and yeah, so the question is basically saying that let tau be an extensive form games with players 1 and 2 whose set of outcomes O can be partitioned into three parts, which are basically the three parts are like either player 1 wins or 2 wins or the game is a draw. So in that case, a strategy S1 of player 1 is called a winning strategy. Uh, Basically, if like player 1 wins, then it's a winning strategy. A strategy and like basically a strategy S1 is called a winning strategy if whatever player 2 plays, like irrespective of whatever player 2 is playing, the strategy S2, whatever is the strategy S2. So for all S2, this strategy S1 should win. So this should be a like winning. This will be a winning strategy. You'll call it a winning strategy when player 1 wins, irrespective of whatever player 2 plays. And similarly, a strategy S1 of player 1 is called a strategy guaranteeing at least a draw. So it's called a strategy guaranteeing at least a draw. If basically whatever player 2 plays, the game ends with either player 1 winning or player 1 or the game ending in a draw. So like this makes sense with the definition, right? A strategy guaranteeing at least a draw is the strategy where like player 1 should win or at least get a draw. Similarly, like these definitions can be extended for player 2 as well. So a strategy guaranteeing at least a draw for player 2 or basically a winning strategy for player. Then now let's consider the following extensive form game. So in the game, we'll call that player 1 is winning if player 1's expected utility is greater than player 2's expected utility. So we'll only be discussing about deterministic settings for now. So forget about these terms, expectation. We'll only be talking about assume deterministic strategies. So yeah, we would the expectation, the randomized strategies will come, I think, in the next week. So for now, maybe we can remove the expected part. Like I thought maybe we can put it because it's what it's called, but yeah, I think it's better to not write it that way. So player one wins if player one's utility is greater than player two's utility. Player two wins if player two's utility is greater than player one's utility, and the game ends in a draw if player two's utility is equal to player one's utility. And then we have to uh, select the correct option in this. So this is the game which we have, and we'll be calling player one as winning if player one's utility ends up being greater than player two's. Similarly, player two is winning if player two's utility ends up being greater than player one's, and so on. So in the game, first player one makes a choice between L1 and R1, and like if player one plays L1, and after this, basically player two gets a choice, and player two gets a choice of playing either L2 or R2. So player one plays L1 and player two plays R2. Then minus one comma one is the payoff. Where basically like the first thing is the payoff of player one, the second thing in the parenthesis is the payoff of player two. So in this tuple one comma minus one here, one is the payoff of player one and minus one is the payoff for player two. Similarly here, minus one is the payoff for player one is the payoff for player two. Similarly for here. So in this game, we have to select the correct options. So options are player one has a winning strategy, player two has a winning strategy, player one has at least a drawing strategy, or none of these. So maybe we can move on these options by options. So yeah, let's just check whether which of the following options are correct and which of these are incorrect. So let's check for option A right now. So option A says that player one has a winning strategy. So let's see if player one indeed has a winning strategy. So the only two possible strategies for player one are either playing L1 or playing R1, right? There is no third strategy for player one. The only possible strategy for player one is playing L1 or playing R1. But then if player one plays let's say player one plays L1, then irrespective of whatever player two plays, player one should be winning. That's what you call the winning strategy, right? But note that if player one plays L1, then player two can just play R2, and basically player one gets a payoff of -1, player two gets a payoff of 1, and then basically player one ends up winning. Player two ends up winning. So player one does not win in that case. So yeah, player one does not have a winning strategy. But maybe we can think about player two then. So player two says, so a winning strategy for a player is nothing but a strategy. Basically, whatever the other player is playing, uh, this player should be uh, winning in the end, right? So the second option says that player two has a winning strategy. So note that the strategies for player two. So first player one is playing and then player two is playing. So note that this in this game, player two strategy will not be actually like discussed in the lectures. Also, player two strategy will not be like just a strategy of playing L2 or R2, but it will instead be a function of what player one plays. So maybe I can just write it. Maybe I should just put the whole question on the next page. Yeah. So option A says that player one has a winning strategy. So this is incorrect, as if player one plays L1, then P1 loses, and maybe I can just say like this: as if player one plays L1 and P2 plays R2, then player one is losing. then P1 loses. Similarly, P1 loses on playing R1 if P2 plays. So if player 1 instead plays R1, then player 2 can just play L2 and okay, then player 2 can just play R2. And again, basically, player 2 will win and player 1 will lose. Right? So uh, whatever player 1 plays, player 2 can just play R2 and win the game. So option A is incorrect. Let's come to option B then. So option B says that player 2 has a winning strategy. So yeah, actually, so uh, what will be the strategy for player 2? So the set of strategy will not be a fixed strategy. Like for player 2, since it's a sequential game, uh, it won't be that player 2 will be playing either L2 or R2. What player 2 will be playing is playing something after seeing what player 1 has actually played. Right? So maybe I can just write this. Since player 2, or maybe just P2, can see what P1 plays, the set of strategies for P2 will be a function of what P1 plays, right? So the strategy for player 2 will not be like actual L2 or R2, but it will just be a function, right? And note that you can actually construct a function here which by which you can make player 2 win. Like whatever player 1 plays, player 2 will win by that function. Like, and what's that function? Uh, uh, Consider the strategy for P2 as follows. So the high level idea is this, like as I said here, as we just discussed for player 1 also. So if player 1 plays L1, then player 2 can just play R2 and win the game. Similarly, if player 1 plays R1, then player 2 can again play R2 and win the game. Okay, so here actually player 2 has a function which is like if player 2 plays always R2, then player 2 will always be winning. So yeah, like here it's a constant function, but in general it will be a function, right? Suppose I switch these payoffs from 1 minus 1 to minus like these two payoffs. Then if player 1 played R1, then player 2 had to play L2 to win if these payoffs were switched. And yeah, so and that is also admissible because it's a perfect strategy for player 2 because it's a function. So consider the strategy for player 2 as follows. Uh, if P1 plays L1, play R2, play R2. And similarly, here will P2 will win. And similarly, if P1 plays R1, again play R2. Here P2 wins. So yeah, so actually here, like whatever player 1 is playing, player 1 plays L1 or if player 1 plays R1, in both of the cases, player 2 is winning. So yeah, P2 can win using the above strategy irrespective of what P1 plays. Hence, P2 indeed has a winning strategy. Yeah. And maybe we should just put a note also that like that actually player 2 strategies is not actually fixed as R2, like it's actually a function. Again, I'm just stressing on this because it's an important thing to distinguish that player 1 will have to play something like L1 or R1, but player 2 is seeing what player 1 is playing also. So player 2 actually has in the strategy space player 2 also has this kind of functions available to him, like of seeing what player 1 is playing. So here the strategy for P2 was a constant strategy, that is like playing R2. However, in general, the winning strategy of P2, if it exists, can be a non-constant function of what P1 plays. So yeah, in general, like in this kind of a setting, it could be a function of what P1 plays. It need not be a fixed setting. Like here we said that playing R2 will land you away, but like if R2 and L2 are switched, then playing L2 would land you a win if player 1 plays R1. And if player 1 plays L1, then R2 would land you a win. Something like that. So yeah, so option B actually is correct, that player 2 has a winning strategy. So if it's clear to everyone, then maybe we can move on to the C part. So C part says like player 1 has at least a drawing strategy. So note that we are talking only about the deterministic strategies, as I've already told. So, and as we have already seen that player 1 is playing L1 or R1, and in both of the cases, player 1 will lose and player 2 will win. So, yeah. So option C is basically incorrect. And this was already discussed in option A. Yeah. And so none of these is anyway like, not true. So what's the final answer then? Hence option B is the only correct answer. So option B is saying that P2 has a winning strategy and P2 indeed has a winning strategy. Option B is correct. Okay, so I hope this makes sense. This was not confusing. That this was also discussed in the lectures. So, but again, I'm still stressing out that player 1 strategy here is some like L1 or R1, but player 2 strategy will be a set of functions. So yeah. And we are just talking about the set of deterministic strategies right now because this is all we have discussed this week. We have not discussed about randomized. Like at least in the lectures, the randomized strategies in these kinds of scenarios have not been discussed. Though we'll try to touch on those a little in the upcoming questions just because we can think about that also. And it's cool to think. But yeah. Okay, then. So we are in the sixth question then. So sixth question says that consider the game of tic-tac-toe where player 1 plays first and chooses one of the 9 squares at random with equal probability. Then which of the following games is which of the following statements is correct? So the statements are it is a dynamic game with imperfect information. So actually uh, the game is not having imperfect information actually. Like uh, as we already told that we have this common data for the questions that the outcomes are either player 1 wins, player 2 wins, or it's a draw. And a winning strategy is a strategy which wins by whatever, irrespective of whatever other player is playing. And a drawing strategy is a strategy which will ensure a draw irrespective of whatever other player is playing. Right. So so the statement is claiming that it is a dynamic game with imperfect information. So actually it is not imperfect. Like everyone knows like so everyone knows that the other player is trying to like so one player knows that the other player is trying to win, right? And they also know like but even though like even if we don't talk about like what player knows about what's the other player trying to do, but we still have perfect information about the utility function. Like we know that when we are saying player 1 wins, player 1 is winning when player 1 actually wins. Uh, and like we are saying it's a draw if basically like if no one is winning. So actually we have the perfect information of the utility function. Like given what I'm trying to say is like given a final configuration of the tic-tac-toe board, like where the game has ended, like you can like any player can like determine who's the winner and who's the loser. Like one does not need to provide like additional information to the player. The players by themselves can also figure out that who has won or who has lost the game. So option A is actually incorrect. So incorrect as given given the configuration of a finished tic-tac-toe game. So maybe given the configuration, by configuration I mean like the final of where one has played zeros and the other has played crosses, something like that. Is if we are given like if a player is given the final configuration as to like the game has ended, but like where are the zeros and where are the crosses, uh, then the player can determine. Then any player can determine by themselves the winner slash loser themselves, the winner slash loser slash winner of the game. Where the game is drawn. So imperfect info. What does imperfect information usually mean? It means that one player does not know the utility function of the other player. Like if like how will the other player be benefiting? But in a tic-tac-toe game, like like if you have won, then the other player has lost, and like if it's a draw, and then it's a draw for both of the people, and something like that. Similarly, if we talk about option B, so player one at least has a drawing strategy. So actually, like uh, okay, maybe I can just remove this part, like playing with equal probability one apart, because it's not really important for us, and I don't want to go into randomizations. Yeah. So the option B is saying that player one has at least has a drawing strategy, and option C is actually saying that player two has at least a drawing strategy. So yeah, well, actually this question does not have like for answering these B and C parts, you really have to know about tic-tac-toe game. That like yeah, whoever player starts first, like there is no way to ensure that there is no single way to ensure that you will always be winning. So there is no single strategy which ensure like there is no strategy which ensures that one player will always win over the other. Like like if both the players are playing smartly, then the game will always end in a draw. Like so actually yeah, these two options are false. Option B, option C, maybe just option B. So this is incorrect as tic-tac-toe game will always end in a draw if both the players are playing smartly. Yeah. So both the players are playing smartly, then tic-tac-toe. This is a property of like not any game, like this is a property of tic-tac-toe specifically. That in a tic-tac-toe game, there need not exist like, there will not exist a winning strategy. Okay. And similarly for option C, the player two has at least a drawing strategy. Okay. Okay, so option B is actually correct. My bad. So I thought it's a winning strategy. Or maybe I can just change that. Yeah. So if option B says that player one has at least has a winning strategy, then it's incorrect because like tic-tac-toe will always end in a draw if both the players are playing smartly. But option C says that player two at least has a drawing strategy, which is correct. Like because like when we are saying smartly, then we are saying that smartly means is having a strategy for something, right? And so this is correct because like as we have said previously that tic-tac-toe will always end in a draw if both the players are playing smartly. So player two at least has a drawing strategy. So due to the reason mentioned in option B, right? So as explained in option B, tic-tac-toe will always end in a draw if the players are playing smart. So not much to think about here. And is it a zero-sum game? So yeah, actually, when you think about it, tic-tac-toe is indeed a zero-sum game. Like if you assign a draw as a 0, something like none of the players is benefiting. Like if you think of draw as a giving a payout of 0 to both the players, then it's a zero-sum game in the sense that if one player wins, the other is losing. If the other player wins, the first is losing. So yeah. So if wins are interpreted as +1, losses as -1, and draws as 0, then it is indeed a zero sum. So yeah, I think this was not explicitly mentioned somewhere in the write-up. Maybe this was missed. Sorry for that, but yeah, like you can call it a zero sum game, like if you interpret these as yeah. So yeah. So actually, option D can be thought of as correct also. So actually, option C and D are correct only. So in final answer, what we have is hence option C, comma D are correct. Okay, then maybe we can move on to the question 7. So I'll just go to the next page. So in seventh question, it's again giving a common data, like it's only one question, but still let's say we have this common data. So the problem is essentially saying that a couple is trying to determine how to spend their time next Friday night. The available activities in their town are attending a concert or watching a football match. The man prefers football while the woman prefers a concert, but both of them prefer being together to spending time apart. So the pleasure each member of the couple receives from the available alternatives is quantified. So these are the payoffs essentially that if both the play if both people like if the couple together watches football, then the pairs are 2, 1. Like suppose man is a player 1, woman is a player 2, then it's the payoffs are in the form 2, 1. Similarly, from concert, the payoffs are 1, 2, and from spending time apart, the payoff is 0, 0. So the couple does not communicate well, so each one chooses where they will go on Friday night before discovering what the other selected and refuses to change their mind. So what this problem is saying is actually uh, each of these people will make a choice, like a simultaneous choice of where they want to go, and yeah, and they'll be going without informing the other person. And now we have to kind of think of this as an extensive form game, or maybe like don't think of it as an extensive form game, but maybe just think about it as a like a payoff matrix. So basically, both man and woman are making a choice between C and F, right? And then you can draw a payoff matrix for the player 1, player 2. And then essentially what we want is to model the game in that manner and then see if there exists a threat or threat surge or something like that. So maybe we'll first try to model the game before the game can be modeled by the following payoff matrix. So what's the matrix for modeling this game? It's something like maybe I'll just yeah. So what we have here is so here we have the strategies. So the strategies for player 1, which is the man, like this is concert maybe, and this is football. Right? So and So the role player is basically the man. So maybe I should just mention. And woman is. Oh, yeah. Okay. Okay. Maybe I should just. I can just speak. And what are the payoffs given to us? So the payoffs given to us are essentially this. So watching if both go to concert together, then the payoffs are 1, 2 because man gets a payoff as written here that one for the man, two for the woman. If one watches concert, other goes to football, then the payoffs are 0, 0. Because like if they are spending time apart, then it's 0, 0. Similarly for football, concert also it's 0, 0. And for football, football, it's 2, 1, 2 for the man, 1 for the woman. So here the payoff is something like 2, 1. Maybe I should just uh, try to make this matrix up better looking. Yeah. Yeah. So these are the payoffs for us. And now the problem statement is essentially saying, answer this as true or false. There's a threat strategy for the girl to coerce the boy. So basically, girl is the woman and like boy is the man. Yeah. So there's a threat strategy for the woman to coerce the man to attend the concert. True or false? So what this statement is claiming is, does there exist a threat strategy like for the girl? So what does threat strategy mean? That the person declares upfront maybe like what they are going to do, even if it may seem irrational. And and if that happens, then the other person has to follow suit. So does there exist a threat? Uh, does there exist actually a threat strategy? So, so as can be seen here, actually, that suppose, okay, and also assume that we are only having deterministic strategies. Assume uh, deterministic strategy. Okay. So there's a set strategy and the players only have determining strategies for the girl to coerce the boy to attend the concert. So suppose the woman has these choices, concert and football. And now we are asking, does the woman have a threat strategy? Like assuming both the players have determining strategy. So can the woman give a threat to the man and then the man has to follow her, her choice? So actually it can be seen that the choices of women are for football and concert. So uh, women can actually give the threat to the man that she will be going to the concert whatever happens. So suppose woman gives the threat that whatever happens, she will be going to the concert. So if the woman is going to the concert, then and if man has to believe that threat, then the payoff for man are like if he goes to a concert, it's 1, and if he goes to football, it's 0. So if the woman has made a threat that I'm going to the concert, then man will have to attend the concert anyways. Right? Because then the man will think, okay, the other person is maybe playing irrationally, like whatever happens, the other player is going to the concert. And then the man will really have to follow suit and go to the concert so that his payoff is 1 instead of 0. So yeah. So note that going to football is not a threat because yeah, like because then the man will prefer football anyways over concert. And the woman wants to give a threat to coerce the boy to attend the concert actually. So if you want to basically attend the man, if the woman wants to make the man attend the concert, she just have to give a threat that she will be going to the concert no matter what happens. And in that case, the man will have to follow suit and go to the concert also. If the woman gives the threat that she is going to the concert, irres- if the woman gives a threat upfront that she is going to the concert, then the man gets a payoff of 1 by going to the concert and of 0 by going to football. Hence, so we are only talking about deterministic strategies, not about like a randomized strategy. So yeah, we'll stick to deterministic strategies. So man has only two choices, concert or football, and then he'll prefer going to concert over football. Hence, the man is coerced into attending the concert. Right. So, so this statement is actually true. Yeah. So I hope this makes sense. Like it can be modeled as in real life also. Like if someone is giving, like basically the woman is giving a threat that I will be going to the concert, and then the person in real life has a choice of like either attending the concert with a partner or like going alone to watch football. And it's always preferable to spend time with a partner, and so yeah, payoff is better than like, going somewhere alone. So yeah, so I think like this is kind of true. And yeah. Okay, then so we have the last question for the day, the eighth question. So yeah, today the questions were quite simple, I believe. Like none of the questions were really technical or anything. Yeah, they were based on this week's lectures. So lectures were like these only. So again, we have the last question. The last question is depict the following situation as a game in extensive form. So like for now, just think of like yeah, extensive form games as those dynamic games which we are talking about. So Eric, Larry, and Sergey are senior partners in a law firm. The three are considering candidates for joining their firm. Three candidates are under consideration: Lee, Rebecca, and John. The choice procedure, which reflects the seniority relation between the three law firm partners, is as follows. So initially, Eric makes the initial proposal of one of the candidates between the three candidates. Then Larry, who can observe Eric's choice, follows by proposing a candidate of his own. And then Sergey, who observes both Larry and Eric's choice, proposes a candidate who may be one of the previously proposed candidates. So first Eric is making some choice, then Larry makes some choice, and then Sergey has to make one choice between the Ari and Eric's choice, Eric and Larry's choices. And then a candidate who receives the support of two of the partners is accepted into the firm. If no candidate has the support of two partners, all the candidates are rejected. So also like here also we'll be considering deterministic strategies. Okay. So the problem 8 is asking then at what proportion of outcome results in the hiring of a candidate? So like what proportion of outcome results in the hiring of a candidate? So what this means is there can be multiple like outcomes like Eric proposing, Larry proposing, Sergey proposing something. And then like, in the end, like one a candidate can actually get into the firm, or like it might be possible that none of the candidate gets into the firm, right? And now we have to see like what proportion of outcome results in the hiring of the candidates. Right. So okay, like here actually what's going to happen is, so Eric makes the initial proposal of one of the candidates, and then Larry, who can observe Eric's choice, follows by proposing a candidate of his own, and Sergey. So basically, Eric, Larry, and Sergey, the three of those are making choices, and like they see the previously proposed candidates and everything also, and after that only they make some kind of a choice, and then we are really asked like in what cases is the candidate accepted into the form. So actually, what one needs to do here is again draw a dynamic like draw this game in the dynamic form by representing like player one as Eric, and like drawing the three nodes, which are the three possible choices for Eric, and then Larry's three possible choices, and then Sergey's three possible choices. Uh, and then just see like what's the uh, ratio in which like some candidate gets hired to like no candidate gets hired. But like actually we can do this orally also. Like I'll draw that also just for, or maybe I guess I will not. I won't. I'll just see. But for now, let's just see like what happens. So right now, what we are claiming is, so Eric makes the initial proposal. Larry, who can observe Eric's choice. So note that the three, Eric, Larry, and Sergey, these three guys don't have any like payoff functions for themselves. Like the payoffs are actually for Lee, Rebecca, and John. That like Lee, Rebecca, and John are the people who will be getting the job. But Eric, Larry, and Sergey, these people don't have any payoff from like which candidate gets accepted. So they don't make like a decision. Like they just make some decisions that Eric says that I like what I think is the best candidate, but it's not like Eric gets a payoff if his favorite candidate gets selected or something. So that's why this is not really that kind of a game. It like you really don't need to think of it as a game. Rather, it's more of a combinatorics problem because like uh, what one can like here, what you can essentially think assume is like Eric, Larry, and Sergey. These three are making choices on their own. Like Eric makes the initial proposal. Larry, who can observe Eric's choice, follows by proposing a candidate of his own. But like it does not mean that Larry gets a payoff if his candidate gets elected or not. So Larry can just so the problem is essentially saying that Larry just presents the candidate which he likes the most. Like he proposes the candidate which he likes the most. Eric proposes the candidate which he likes the most. And similarly, Sergey proposes the candidate who he likes the most. So essentially, three of these guys are proposing the candidates which they like the most. And what proportion of outcome results in the hiring of a candidate. So you kind of really don't know like so Eric has three choices to make, right? Eric has three choices, Lee, Rebecca, and John. Larry has three choices, Sergey has three choices. So all these three people have three choices each. So there are actually three times three times three. So there are 27 possible outcomes overall of like the kind of proposals which can go through. Like it can be that Eric chooses Lee, Larry chooses Lee, Sergey chooses Lee. This is one outcome. One outcome is Eric chooses Rebecca, Larry chooses Rebecca, and Sergey chooses Rebecca, uh, or something like that. Okay, but okay, so I think there's another element in this problem that yeah, maybe I should like yeah, then this problem just becomes a combinatorics problem that there are 27 choices, right? And out of these 27 choices, like we have to count the proportion of where at least one player gets at least one of Lee, Rebecca, and John gets 2 votes, right? So note that since there are 3 people, Eric, Larry, and Sergey, all 3 will be voting, and so like total 3 votes have to be distributed between Lee, Rebecca, and John, right? And so note that if no player is getting support of 2 partners, then each of these is getting support of only one partner. So okay, maybe I should just mention it here, like 2 of the partners is executed into the firm. Okay. Note that the support for the candidates is counted. Okay, maybe we can draw this as another question rather right now. Uh, so what I'm kind of thinking here is okay. So what we can think of here is Eric, Larry, and Sergey are making independent choices, right? And then you have like these 27 kind of way outputs, and out of those you have to see like which partner gets accepted into the firm or not. But there can be another thing that like so if Eric and Larry have already elected a candidate, that if Eric and Larry together have 2 votes for some candidate, then suppose Sergey's opinion is not even counted. So that can be one way to like that can be another way to look at the problem. So that's what I'm kind of trying to mention here, that if the votes for the candidates are counted at the end of voting by all 3 seniors, then what proportion of outcomes result in hiring of a candidate? So this is one question which I meant, and a second question can be this kind of a question where okay, maybe it should. Yeah, yeah. The second question is something like if so what I'm trying to say is what one can see is like if Eric and Larry vote on something, uh like suppose Eric and Larry have voted already on some candidate, suppose both have voted on Lee, and so Lee we already know has support of 2 of the partners, so he will be accepted into the firm. But in that case, do we count the opinion of Sergey still or not? So it's like, is Sergey also allowed to vote at the time, and at the end we are counting the votes? So suppose votes for the candidates are counted at the end of voting. So this means that all 3, Eric, Larry, and Sergey, get to vote. But note that there can be another possible pattern, like which you can think of about seniority, that if the candidate, so what another thing can be like if Eric and Larry have together 2 votes for some candidate, let's say Lee, Rebecca, or John, then opinion of Sergey is not even counted. So we don't even take Sergey's vote in that case. And that is a bit trickier to model because now, like in some cases, if Eric and Larry together have like one votes for 2 candidates, then Sergey gets to vote. Otherwise, Sergey does not get to vote. And in that case, the total number of outcomes is not really 27, but something less than that. Because in some cases, Sergey is not even voting. And that I'll try to show using the dynamic range diagram. But for the first part, I won't be doing that. But maybe I should just mention the questions. If if a candidate is elected as soon as he or she gets 2 votes, and further and then further voting gets stopped. That is, if Eric and Larry uh, vote for same candidate, then Sergey's opinion is not even asked. Okay, so these are two frameworks. In one case, you are always counting Sergey's opinion. There can be another possible mechanism in which Sergey's opinion is only asked if Eric and Larry fail to land on the same candidate. So in both of these cases, what proportion of outcomes result in hiring of a candidate? So here, like in the first question, it can be seen that every senior has three choices because the three candidates are Lee, Rebecca, and John. Maybe I should just mention this. That is Lee, Rebecca, and John. Hmm. So the probability that so what proportion of outcomes results in hiring of a candidate? So total number of outcomes is total number of possible outcomes. Maybe I should just, yeah. So what's the total number of possible outcomes? It's something like 3 into 3 into 3 because there are three people and 3 into 3, which is 27. And number of outcomes. So I'll be doing this really quickly because it's more of a combinatorics question. So number of outcomes resulting in no hiring is equal to. So what are the cases when there won't be any hiring? So there are three votes. So like suppose all the three votes are divided, one each for these candidates. So Lee gets one vote, Rebecca gets one vote, and John gets one vote. So all three get one vote each. But how many such outcomes are even possible? So it can be seen that actually this is possible by so if all these candidates are getting one vote each, then Lee gets vote of either of Eric, Larry, or Sergey. So there are three choices of Lee getting a vote of one. But as soon as Lee gets a vote, then Rebecca gets only two choices, and then John only gets one choice. So 3 times 2 times 1, which is 6. So number of outcomes resulting in hiring is actually equal to 27 minus 6, which is 21. And so what we get is a fraction of outcomes resulting in hiring is actually equal to 21 by 27 here, right? Which is something like 7 by 9, right? So here actually you can see that the fraction of outcomes is 7 by 9. But now we'll try to model this a bit differently. Like in the second model, if a candidate is elected as soon as he or she gets two votes and then further voting gets stopped. So it means that if Eric and Larry vote for the same candidate, then Sergey's opinion is not even asked. So again, you can draw using combinatorics. Like you can again have some combinatorial argument, and here consider the cases where Sergey's opinion is ours and not ours. But I'll just like to show a like since we are discussing about dynamic games and stuff, I'll just like to show a diagram for this. So maybe we can draw up a diagram here. So let's just suppose the first node is so first opinion is asked by first Eric gives an opinion. So first player is Eric, and maybe Eric needs to be written. Yeah. And what choices does Eric have? So, okay. So Eric has three choices. So maybe I should just. So first choice is Eric's, and Eric will give. Yeah. So there are three choices for Eric, and the choices for Eric are the three layers actually, the three candidates. Maybe I should just, yeah, put these a bit. Yeah, now it looks good. I'm just trying to focus on the aesthetics a little. Yeah. So first, Eric gets a choice, uh, and Eric can elect either Lee, Rebecca, or John. Eric can vote for Lee, Rebecca, or John. Right. And now the second player is essentially Larry. So it's not Eric, but Larry. So now Larry gets to play. Similarly, Larry and Larry. And in all these three cases, Larry has three choices each again, which will be again like something like Eric, Rebecca, and Lee, Rebecca, and John. Maybe I'll just copy all of this here. And yeah. Okay, maybe I should just. Maybe we can put it a bit sideways so that it does not mess with the other thing. So Larry has three choices, Lee, Rebecca, and John. And note that here, if Lee gets two votes from Eric as well as Larry, then here we can just directly say that like Lee wins. Here, like if Eric gives a vote to Lee and Larry gives a vote to Rebecca, then choice of Sergey is also asked. So here we'll also be asking Sergey's choice. Maybe I'll denote the outcomes by a different shape than a circle. So here maybe we can say that. Yeah. So it's 16. Yeah. In this case, Lee wins, and yeah, in this case, opinion of Sergey is asked. So this is Sergey. Sergey's opinion is asked here. And again, Sergey will have three choices between Lee, Rebecca, and John. So maybe I should just again have like yeah. So then like after Sergey is asked here, then like there will be just outcomes, right? So we'll just copy these three outcomes here. So yeah, this is the diagram is a bit complicated, but note that like the problem is actually not that complicated. So if we have Sergey here, then Sergey, if Sergey votes for like suppose let's say Sergey votes for Lee, then Lee will actually be winning, right? But if Sergey votes for Rebecca, then Rebecca will win. So if Sergey votes for Rebecca, then Rebecca will win. So yeah. And but if Sergey votes now for the third player, which is John, uh, then actually no one will be winning because now all three have in this path all three have voted. One has voted for Lee, one has voted for Rebecca, and one has voted for John. So in this case, no one wins, right? And now, so Sergey's decision in this case, like there can be some cases where no one wins, and now similarly, uh, one can have this kind of a thing for here also. Maybe yeah, we should really be expanding these out. Otherwise, it will be a nuisance. Yeah. And now, if Eric had voted for Lee and Larry had voted for Lee, then Lee actually won. If Larry had voted for Sergey, and then then actually this kind of a thing works. And in this case, I'm just trying to make it a bit more aesthetic, that's all. But yeah, this is the high level idea which we have at yeah. So what we have here is Eric voted for Lee, then Larry voted for John, and now Sergey's opinion will be asked. So if Sergey votes for Lee, then Lee will win. If Sergey votes for Rebecca, then no one wins here because like no one is getting a majority. And then if one votes for Lee, the other for John, third for John, then here John will win. And note that you can actually. So I've just drawn this one part, but similar things will be happening in other outcomes also. Like in other outcomes also, like you will have like the kind of proportion will actually be maintained that. So here what happens is like so there are like 7 possible outcomes in one outcome. In one outcome, Lee like so there are possible 1, 2, 3, 4, 5, 6, 7 possible outcomes, and out of these like we only have a non-winner in 2 of the outcomes out of these 7 outcomes. Like here we know that Lee is winning, here we know Lee is winning, here Rebecca is winning, here no one is winning, and similarly here no one is winning. So so out of these 7 possible outcomes, we only have 2 outcomes where no one is winning. Right? So and like this kind of similar thing will also carry over here also. When if Eric chooses Rebecca, then Larry will have the choice between these 3, Lee, Rebecca, and John. And this kind of a graph will transfer over here also, but with different labels. So maybe yeah, this graph can be a bit confusing. So let's leave the graph at here. Otherwise it will become a bit messier. But the high level idea is no one is winning only in 2 out of 7 scenarios here. And similarly, there will be 7 scenarios here where no one will be winning in 2 of those. Similarly, 2 here. So here, uh, like, so in hiring of a candidate, like it can be seen from the diagram that a candidate is not hired in 2 out of 7 cases. Hence, so maybe just fraction of proportions resulting in hiring is actually equal to 5/7, which will be, yeah. So maybe we just write like that. So actually this will be the answer, that the fraction of outcomes resulting in hiring will be nothing but 5/7, as can be seen here that there are 7 possible outcomes and 2 of these result in no one winning. Other than that, in all of the like at least one is getting hired. And this similar kind of a graph will carry over here also when Larry makes other choices. Okay, so I guess this makes sense. I'll also like paste this graph into this document while uploading this document. This is question 8 and 9. Okay, then. So I guess this was all I had for today. These are the set of questions which I had for today. So today, like mostly the questions were theoretical and like not too difficult. The numerical were also very straightforward questions. So yeah, but the last one was also not a tricky question, just some basic combinatorics and stuff. Like you would have derived this thing using combinatorics also. Like it would not have, it is not difficult at all. You can do this yourself. But I just wanted to give like draw at least one graph for a game because why not? Okay then. So I hope so no one is present in the session in person here, but yeah, I hope everyone is clear with. I hope whoever was watching on YouTube, everyone is clear with whatever was discussed in today's session. So I guess this is it for today's session, and hopefully I'll see you guys next week in person in the sessions. So yeah. So till then, goodbye everyone. I'll be stopping. Bye. I'll be stopping the video.